Miss Jody here with our second video for our physics STEAM class. Today, last time we talked about, we were finishing the chapter on the electromagnetic spectrum, electromagnetic waves, and understanding the production of radio waves and how all that worked with the AM and FM frequency. And now we're moving on to light. Now, light, we're going to spend a lot of chapters studying light. And this particular chapter in the basic physics is the chapter number 18, I think. And if you remember, we're still taking our notes on a half sheet. I grabbed a half sheet here. So make sure you're still taking your notes on a half sheet to glue in and write the title on the back of the half sheet so we can keep track of it. Now, there is a PDF diagram that goes along with this chapter that I'm sending you, and it has two not diagrams but lists basically of the history of our understanding of light, and that is to be printed out. Actually, you might not have to print this one out because there's no real coloring diagrams like that you have to color in. It just has the prism experiment, and then it has the on the second one, it has the frequency of red versus orange, yellow, all the different lights. So that's just for decoration. So you really don't have to print that out. So because I will print these out and have them in your journal already. But for reference, you might want to print it out just to keep track of some of these dates. Because what we're going to do with this introduction to light is just take a look at the questions, why people started looking at light and what they wanted to understand about light, and then like a brief history of how people started looking at it differently over the years and the different experiments that took place in trying to understand light. So these two sheets that are the diagrams of the lesson are just those a few things kind of listed in order so that we can keep track of when we're talking about different experiments and different scientists, we can try to put them into their time frame. Okay, well, who was thinking what at this time? Okay, so you don't necessarily have to print those out if you don't want to waste your ink, but if you want for reference. Okay, so light. So we start as an introduction. So I just noted the questions begin because there was a lot of things that people were starting to wonder about light. What is it? How does it behave? Is it governed by laws and rules? And at this time, the laws of motion hadn't really been set by Isaac Newton, but there were other scientists starting to put together rules and laws of the physical world as they did their experimenting and their thought theories. And so is it governed by a set of laws and rules that we have to figure out? Can it be measured? How do we see it? Like, how does the eye work? There was all these questions, is light, can you measure it? Does it have a speed, or is it infinite? Like, is it always just there and then it's there and then it's not there, and lacking light being the dark world? And so there was a lot of questions that began to be raised. And of course, curious scientists of the day wanted to figure these things out. And so when we look at the diagram that I sent you, it's just going to have a little kind of blurb writing. And I took this from a website that just gave a little history of the understanding of light. And there's a lot more that's went on in between each one of these, and even some that our book brings out that we have to kind of add in. But I thought it would just be a good reference point. So we could kind of say, okay, when we start talking about Sir Isaac Newton, so we can kind of remember time frame of where he's at compared to back in the 1600s with Robert Hooke and some of those guys. So we can just figure out who's where and what and give us a good reference point. So if we look back at what people were starting to think and what they were their theories of putting these things together. So in 400 BC, this notes the emission theory of vision. And so some Greek philosophers and mathematicians of the day were already starting to ask those same questions about light and trying to figure them out. And Greek philosopher and mathematician Plato, which we've talked about him a lot, he develops the emission theory of vision, which is we see because our eyes emit straight vision beams. So if you've ever seen this theory before, it'll show a person, and from their eyeball is these beams of light. It makes me think of some of those characters in sci-fi movies who can beam out light. And so this was the idea, is that we were beaming out the light and we were able to see because our eyes were the source of that. And then later on, years later, and there's a lot that went on in between these two time frames, obviously, because look at the dates, but we're just pulling out a few for reference point. Ptolemy began to look at the world of refraction. Roman astronomer Ptolemy writes about the refraction of light and further develops the emission theory of vision. So still working on this theory, he begins to look at how it's refracting and how maybe the eyes worked in the emission theory of vision. Objects are seen by rays of light emanating from the eye, like that particular theory. And so it began to continue on, and of course between this year and this year we have a lot of years that have passed, and so more scientists, more people that were curious. And again, this is just not a thorough study of everything, but just bringing out a few things. Excuse me. Ibn Sal, I don't know how to really pronounce that, a Persian scientist, Ibn Sal, writes on burning mirrors and lenses. And in this, it sets out his understanding of how curved mirrors and lenses bend and focus light. And he discovered the law of refraction, mathematically equivalent to what is later known as Snell's law, which you'll see down here with astronomer Wilbur Snellius. And so he ends up putting it together mathematically, but this is the introduction to the whole law of refraction. And then as we move on, then in the intromist theory, an Arab scientist, Ibn al-Haytham, and so two Ibnams there, contended that vision occurs because of rays entering the eye. So instead of the eyes putting out the light was coming into the eye. And he also contends that the magnification is due to refraction, and he makes the link between glass curvature and magnification. So they start figuring out, basically thinking about just how light works in the sense of how we see it. And then later on, Roger Bacon and the world of reflection, English philosopher Roger Bacon uses parts of glass spheres as magnifying glasses and discovers that light reflects from objects rather than being released from them. So again, we're moving on into a different way of looking at things as time progresses. And then continuing on how the eye actually works and their ideas of how the eye works, German mathematician and astronomer Johannes Kepler, which we always talk about, describes how the eye focuses light and specifies the laws of, I always say this wrong, has the eye in the middle, rectilinear, I can't say it. Well, rectilinear propagation of light, which all that means is just straight. Okay, I should just say that. Okay, straight propagation. We know what propagation of a wave would be, in that it was going in a directional straight. So, and then later, this Dutch astronomer Wilbrord, can't say that either, Snellius, he's first accurately described this concept, this law that he ends up is by this guy, him, right here, describes the relationship between the angles of incidence in refraction when referring to light passing through a boundary between two different media. So this is the idea of when light goes through something else compared to just the air, or light going through water, or passing the boundary in the movement when in line with what had been talked about in this area of refraction. And so then the next one is in 1668, the corpuscle theory explained, the corpuscular, which is the theory that light is made of these little corpuscles. So Isaac Newton explained that the theory originally set forward by Pierre Gassendi, that light is made up of small discrete particles called corpuscles, to claim that light is made of different parts. And also, I just put along the side here, Hooke was involved in this idea back in the 1600s of that light is a wave, and that was starting to look, because of the way it refracted and stuff, it had wave-like behaviors. And then Descartes, if you remember him, he was also involved in the this theory with the corpuscles and trying to figure out whether that was right or wrong. And so there's a lot of people that have been put in each one of these in-between categories. So this gives us a reference point of who's looking at what when, okay? So going back, in our book, it starts talking about, okay, once they wanted to figure out what is it, how does it behave, what are the rules, can it be measured, those sorts of things. Along came the idea that maybe light could be measured, and of course, Galileo Galilei wanted to try to measure that, and they give us a time frame around 1600, the year 1600. So if we look back over here, this is the time when Kepler and all these guys were starting to figure out, or trying to figure out, this light stuff. So in that same time period, Galileo Galilei, he tried to measure the speed of light, and this is how he did it. And if you remember in the book, so he stands on one hill, and then a few miles away he has his friend stand on another hill. And he says, basically, when I turn my lantern on, then when you see my light, then I want you to turn your lantern on. And then all I'll do is I'll turn my light on, thinking maybe light traveled a little slower. I'll turn my lantern on, I'll watch my clock, and then after a certain amount of time, then I'll see your light go on, meaning the light finally got to you. Now, obviously, it doesn't sound very reasonable to us, because we already understand the speed of light to be very, very fast. And so there wasn't enough distance here for that to happen. This is only a few miles, so to speak. And when it comes to the speed of light, we're talking about it being able to travel so fast, tons and tons of miles, right? So what is it, 186,000 miles per second? So how is he going to even measure this if this is just a few miles? Because in 1 second time, it would have been able to travel already 186,000 miles. So this, but of course he didn't understand this, but what this did help him conclude is that it was too fast for him to measure, and they only had the certain clocks back in those days. You know, he's the one with the pendulum clock in the first place, and so they had limited ways of measuring things, and this obviously just weren't far enough apart. But the thing is, he couldn't rule out, because it seems so instantaneously, he couldn't rule out the possibility that it moves instantly from place to place, because some theories were saying, oh, you know, it has an infinite speed, and so you can't really measure it. It's just always is, always there, and there it is. And so he said he couldn't rule out the possibility that it moves instantly from place to place with infinite velocity. Excuse me. And so that was an attempt, and that shows a lot of thought on his part, that, you know, he wanted to figure these things out. He was the scientist that we always talk about of taking the step to leading himself and others into the area of experimentation, not just being great thinkers, but trying to figure it out through doing experiments. Then our book goes on to Olaus Romier, I think it is, Olaus Romier, 1675. So if you look at the time frame as a reference, it's around this time, a little after this corpuscular theory is explained, and so Sir Isaac Newton's time frame. And so they give him the honor of saying he was the first successful measurement of the speed of light. And his method was based on astronomical observations. And what he was doing, he was looking at the moon of Jupiter that we call now Io. Okay, so Jupiter's innermost moon. And so if you look at this little diagram, this is my attempt of drawing it out, so we'll hope it works here. But here's Jupiter. So here's my little Jupiter. And then if you look at it, you see that there is this little dotted little path around. And that's me. And you see the same diagram in the book. This is me trying to show, okay, Io's moving around Jupiter. And this line is supposed to represent the orbit of Jupiter as it's going around. And so here's the sun over here. And then, of course, here's Earth, a little farther away from Jupiter. And so as you're on Earth and you're trying to look, and you're pointing your telescope to look at Jupiter, as the moon passes in front of it, you can calculate that rotation. And so he was able to calculate that from this perspective, looking at that moon rotating. So he realized every 42.5 hours it would rotate. And so he said, well, then now that I've figured this out, that what this rotation is, I can always see this rotation no matter what in 3 months from now, 6 months from now. But as he continued his calculations, he started realizing, excuse me, that he was getting some different numbers eventually. And what was happening is, if you see Earth right here, then now if you see Earth moved over here, this is Earth going in its orbit. Okay, so as it goes in its orbit around the sun, which obviously would be more elliptical than what I've got here, when the Earth is in this position all these months later, then when he's pointing his telescope, still looking at Jupiter over here, then the light is going to take a little bit longer for him to get there to for this particular observation of the rotation of Io. And so this distance between where Earth was and where Earth is now is the distance that the light would have to travel a little farther. And what he concluded is that it took 500 seconds longer for this, 500 seconds later than what he thought it was going to be, because the Earth had actually moved. And so by using that, now he did not have a real true definition, or distance from the Earth to the sun like we have a better calculation now. He didn't have that, but he did have a certain calculation. He said, okay, well, now that I know, and I'm thinking, okay, it's just the light's taking longer to get there, all I'd have to do is take the distance between the Earth and the sun, and I'd divide it by the 500 seconds more that it took. And that would help me give a calculation about how fast light is moving. And so he took and did his calculations, and it wasn't accurate because he didn't have the Earth to the sun distance accurate. But then later, when we had a more accurate Earth to sun distance, which we would say is 93 million miles on average, about 93 million miles away, and you take 93 million miles away and divide it by 500, what do you get? The distance divided by 500 seconds, you get 186,000 miles per second. And so it is accurate in that sense, if he would have had a better accurate there. So he kind of gets that little accolade there for trying to figure that out. Pretty wise. That was brilliant. So that begins to say, okay, now that we know that we can measure the speed, then we know that it isn't just there. It's just traveling. And so the idea is that light has a property that's like waves, because waves travel. And so, of course, illustrating the wave theories, and the next diagram, it continues on with some of these things. And we're going to stop right here at this point with the lesson in the sense of this diagram, because the next chapter will go on and continue some of these. But I went ahead and just put them on there for a reference point. And so, as we're continue on and they start realizing, oh, wow, you can measure it. It does have a speed, and we're starting to figure these things out. There was also some ideas of it not necessarily being just a wave, because though it was exhibiting wave properties, there was other things that were kind of making it seem like it had to be more than a wave. And let me just go back to this one for a second, and the corpuscular theory expanded by Sir Isaac Newton, thinking that the light had to be more, it had to be something more, and that his idea was these little discrete particles. Again, it wasn't just his idea, because there was a lot of other gentlemen working on this, but he kind of explains it and puts it all together. And so the wave theory of light, that wave was behaving like a light with speed, like a wave with speed and all that. And then the idea is, well, wait, it does have wave-like behaviors, but it also seems to be like it has particle behaviors. And so obviously Sir Isaac Newton, he just demonstrates, he starts doing his experiments with the prism, this famous experiments with the prism, and he's able to separate the light into a spectrum of colors. And he develops the idea that the different colors of light being absorbed and transmitted and reflected. And he puts his book together, Optics, and is released to the public in 1704. Now, when Isaac Newton is looking at this, he has some reasons why his idea of this particles would fit this, what he was seeing with his experiments. And I'm going to move over to this page to explain that, so we can get a feel for that theory, and then also the other theory that was building of the time, that light was actually a wave. So what it's going to come down to in our introduction to light is the two main theories of the day. So we had the wave theory of light, and we had the particle theory of light. So I'm taking these numbers back, and these are back on the timeline, but just in the idea of whether it's a wave or a particle, I thought, well, I'm going to give some basics of these particular two, okay? So as the wave theory of light, Robert Hooke was one of the gentlemen that was really into thinking that light was of the wave nature because the way that it behaved, all the way back to the 1600s. So he's way back, if you look back on the diagram, he'd be over here in this time period here. And so he was thinking it was a wave. And his theory was sometimes referred to as the pulse theory. The theory is that light spreads like water waves. And so if you think of a water wave in the way that you drop a little pebble in the water and then it begins to move out in that wave-like manner, he suggested that light was doing the same thing. And he suggests that light's vibrations could be actually perpendicular to the direction of the propagation. So if you remember transverse waves, if you're a transverse wave, then you are going to, your vibrations, your up and down, your oscillation is going to be perpendicular to the propagation of the wave. So remember, we always do that 90 degrees. So up and down is your oscillation, and your waves moving this way. So he was already suggesting in this idea that light was a transverse wave, as does James Clerk Maxwell in Huygens or whatever, however you pronounce him. All right, so then with the wave idea, Christian Huygens, now one of the videos I'm going to send you, I think he pronounces it Huygens. I forget how he pronounces it, but it doesn't sound like anything I once called him. And so who knows how you're supposed to... and even Descartes, he calls him something else. And I'm like, well, with my pronunciation, who knows? All right, so Christian Huygens, whoever that, or however you pronounce that, is a part of this wave theory idea. And he mathematically creates this formula and has the mathematical wave theory of light. So able to take light and put it into its mathematical perspectives on how it behaves. And he said it is emitted in all directions emitted in all directions as a sense of waves in a medium. Oh, I think that's supposed to say as a set of waves. I don't know what that's supposed to say. I think it's set. Maybe change that. Direction as a set of waves in a medium. All right, well, anyway, so he thinks basically that light is going out in all directions, and as it's going out in all directions, it's moving through this invisible medium called the luminiferous ether. And you've heard of that, and our book talks about the ether theories. The idea that as up to that point, anything that was a wave had to have something to travel through. Sound had to travel through something. Waves needed a medium. So the fact that light was traveling, what was the medium? So the idea and the theory was, it was this ether, this invisible ether that is everywhere that light is traveling through. And of course, as we went along, as you see in the book and as they went along in the history, they started saying, if it was an ether, if it was made of a material substance, like what we see with air and whatnot, then as light would move through, there'd be friction. So just like as everything moves through in regular media. And so there was a lot of things that had to be looked at in the ether theory. And then also in the ether theory, light being able to move through like the gases themselves as they were vaporized. And so looking at like, well, is there ether inside the gases, or where's this ether? And so there was so much that went into understanding this ether side of things. But at this time, the idea was that light was a wave and it was moving through this special ether. Later on, Thomas Young, he's the gentleman who does the double slit experiment. And our book actually refers to it and tells us to look forward to chapter 22 to look at this experiment. And I would normally have put a diagram in and went over the experiment for a diagram of the page, but since we will be going over this, the diagram's going to be in when we go into chapter 22, but I thought I would just look at it here and do it inside my book so you could get a feel for what they're talking about. So in chapter 22, because what's going to happen is we're going to be introduced to light, and then we go through all of these things, like how does it behave? Is it a wave? Look at all the things about the wave world. Is it a particle? Let's look at all the things about the particle world. And so that way we can get a good sense of it, right? And so with this diagram, I'm just going to use my colored markers in here and do it right in the book just to for you to get an understanding. The double slit experiment. So basically, in the beginning, and let me use this highlighter this is a source of light here. Make sure you can see this. So here's a source of light, and the L is the light, okay? So the light's coming out, and as they're drawing this as light as a wave, okay, they have a little piece of cardboard or whatever it was, I can't remember what it was, and it had two little slits in it. See the two little slits in there? And so those two little slits, light's going to be able to get through. And when it gets through, what they were tracking on is what ends up happening on this board here that had some I think might have been like photo paper that was able to sense the packets of light, or the light itself. And so they were shining it on that through the slits. And I think on the video, one of the videos I send you, it actually recreates this experiment so you can see it. But to make it simple for you to understand so that you can comprehend while you're doing that and take it all in, the lights, the way that they're drawing out in this diagram, if you have a full line, they're saying as a wave properties, because they're saying it's going like this, okay? Like this, like this, like this. But in order to draw lights out, or the crest and the trowels, they're going to have to do this dotted. So let's say the dotted is the trowel, and let's say the straight line is the crest, okay? And so when it's drawing, and this is why I'm gonna need like two colors to do that, I'm gonna have how about I do like the big line, that will be the straight line, will be the crests, okay? So as the crests are moving through, and then the dotted line would be the trowel, and this one already has yellow on it, so you won't be able to see it, but once we move through the slits, then I'm gonna keep the yellow and the orange together, okay? So as the light is being shown onto this area, and there's two little slits, the light begins to come through, right? And as the light comes through, we have the same thing happening. Now this little hole in the light, and let me make sure that this is visible. I might have to do this a little bit closer here. Okay, so this little hole there and this little hole. So let's just do this one first. So this little hole here, as I'm coming through, if I have a total straight line, I'm gonna do orange, and then see the dotted line, this is the wave coming through just that particular hole. The dotted line is gonna be the yellow, then this would be the next straight line, and then the dotted line will be the yellow, then this would be the next straight line, and then the dotted, and then the next straight line. And that's representing the crest and the trowels. And so then it gets mixed up because you got light coming through here too. I'm still just focused on this first slit. So then the second one here is the light, that's the trowel of the wave. And then that's the trowel of the wave, and that's the trowel of the wave. And so that's just going through the first slit. But then what about the light that came through this slit? We've got to redo that. So then we have the crest, straight line, crest, straight line, and then don't forget to skip over the light, which would be the trowels. There's another crest up here, and then there's another crest there. Okay, and then the trowel would be the dotted line, which would start here, dotted, the next set of the trowel there, and then there. And then basically, as the light was moving through between the two colors and the two slits there are times when the light crosses over and actually touches where both of these, because the light coming this way and the light coming through that way and making its little ripples, sometimes they touch each other and they're of the same, meaning they're of the same crest. And there's times when it touches in there the crest and the trowel. See this little dot here? This is a crest of one light, but it's also the trowel of the other one. So when the crest and the trowel meet, it creates the interference, like we talked about when we looked at the characteristics of waves and wave properties. But when they actually meet together and they are of the same, so like say for instance this right here, see this is a crest, orange, and here's another crest from this other light, from the other slit, and they meet together. So when they meet together, they would be creating a coming together, which would make it increased, right? And so as the light was being shown through, in the end, these lines that were, and let me get my highlighter for this one, but the lines on the the wall or whatever, the paper, whatever, you would have a line here, and then see the dotted line? You wouldn't have any, and then the one that was straight, you'd have one here, and then the dotted line you wouldn't, because it didn't come together at the right points. It was yellow and orange, yellow and orange, yellow and orange. And then the places where it did come together, where it was orange, 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 it was creating the light to be shown through. And so what would happen is, in the end, you would have lines on the black and white skipping over each other. So you'd have the lightness and the dark, and the lightness and the dark, and the lightness and the dark, and so on, of how many of them got through. So with this double slit, what they call the double slit interference experiment, the idea was this is acting just like waves do, and that we've already measured in wave properties and how they interfere with each other, and the properties of interference and diffraction. And so when they saw that, they said, well, it's got to be a wave, because look how it's doing the same thing that other waves do. And we'll talk more about that particular experiment and others that were like it, that were starting to make them think of the possibility. So by seeing the constructive interference, where they were coming together and both meeting each other, and it was constructive, versus the destructive interference that we saw, and when we studied like sound and all the rest of the waves. So that's kind of cool. Now, along with this wave idea, then we had those who were saying, no, it's a particle. And of course, Sir Isaac Newton, which we already explained he was on the diagram with understanding his theory of the theory that he perfected, other men's theories of corpuscles, and also then his prism experiments. And when he did his prism experiments, he thought each color corresponds to a certain type of particle. So trying to put the light theory into the particle world, he said these different lights that I'm seeing come out of the prism, it's because they're made of different types of corpuscles, different particles. And then when you get white light, it's basically it's a whole packet of all the corpuscles coming together, the different types of particles coming together to make white light. So he was trying to put together this idea of these different particles inside these, as a theory of what light was. And then he thought each passing through the prism at different times, at different speeds. And so he thought the prism worked by the way that light was passing through it, and then depending on the different particles, it would bend them differently because of the speed of the particles. And so you'd have all these different colors coming out. And so this idea was taking some began to start to take some speed, and of course back and forth between those who believed it was wave, those who believed it was particles. And then of course there was the problem with what we call the photoelectric effect, and this is one of the things that the wave theory was having trouble with explaining, where the particle theory was doing a little bit better at it, they thought at the time. And so the photoelectric effect, and you've seen this in your book, is the idea that if I create a circuit here, and I'm going to pull this up just so it's a little bit closer here for you to see. And so if I create this circuit, and I have, this is like my little geyser count, or not geyser, but my little measuring current. And so I have my little meter here, and I've set up my positive and my negative, and I create the current. And as I'm going, at the end of this negative terminal, I have a metal, sodium metal. And so, and then in between, then I have a 1 centimeter in between. And then on this end, I have another type of metal. And I take both of these and I seal them off into a sealed off container with no air. And then I do an experiment with this circuit. Now they're not touching, so the electricity shouldn't be able to flow, right? And it doesn't. In the dark, normal, where there's no light, there's no current that flows that's measurable. But then the moment you put light onto this sealed off thing, the current actually flows from this end, hops over this area into this metal, and is able to complete the circuit. So by doing this, they started to realize that light was somehow, something that was coming from the light was able to push the electrons to bump them enough to where they could cross this barrier and actually create a circuit. And they realized that if there was more light, if they put more light onto the plate, it created more current. And they realized that the higher the frequency light, so we have our frequencies of light, which is obviously talking wave properties, but still, we have red, orange, yellow, green, blue, indigo, and violet. This is the Roy G. Biv of the visible spectrum. And they realize that if you are farther down this way, that it has a better chance of getting these electrons to actually jump over. When they would shine the red light on there, which is the lower frequency, but actually longer wavelength, they weren't getting this. They weren't getting the current. But if you were using the higher frequency lights and even past violet to ultraviolet, then you were having this success here. And so there was some things that were puzzling about this photoelectric effect that didn't seem to be wave light, because they were saying, okay, well, if light is a wave, it doesn't matter how frequent it is, it's still all just kind of flowing there as if it doesn't have anything on it. And so the idea of light being particles, that the more you have, the higher frequency you're getting hit by those particles, then it can hit them, and then the particles can jump over, the electrons can be bumped out and moved onto the next metal and creating the circuit. So they weren't exactly sure how it all worked, but they just thought it didn't really fit with the wave theory as much. And we'll look at more in depth with that when we study the actual whole wave theory of it and then the whole light theory of it. This is just an introduction to the battle of understanding what light is. And so that leads us to the end of where we're at on our diagram. Colors being explained by Sir Isaac Newton with the prism, the wave theory being pushed, Christian Huygens, and arguing that light consists of waves, and uses the theory to explain double refraction. And it uses eventually Tom Young's experiment in 1801 supports Huygens' theory. So later on, many years later, we'll support that theory. And then, of course, which we've already talked about, into the electromagnetic field, James Clerk Maxwell explaining that electricity, magnetism, and light are all manifestations of the same phenomena, the electromagnetic field. And of course, if you remember, once they were able to measure the speed of light, they were able to realize that it was the same calculations that they were getting for the speed of the electromagnetic waves. And so they were like, wait, okay, maybe light is an electromagnetic wave. So there's a lot of things that we're linking to all the different theories that eventually leads us into the theories that we have today, which we'll talk about in our next video. Okay.